Hello and welcome to another video. So in this video, well, I know I have been absent for 2 years on this science channel and now I'm back. So how are you doing? Basically, so now it's May the 17th, 2020 and a lot of countries are suffering from COVID-19, now it's like year 2, the second year of COVID-19 pandemic already. Right, so I have some more time, so I can work on more science videos. So probably I hope that I can expand this channel in the same way that I did to my IELTS channel. So of course, the link to my other channels, you can find it down in the video description below, okay? So I have my piano channel, the old one and the new one. I have my science channel, this one. And I also have the IELTS test prep channel, English testing, system channel. Right, so in this video, I will show you something that I should have done a long time ago. It is called molecular shape and geometry. So this video is in the part of inorganic chemistry, and I assume that you have watched the other videos already in the same series before you approach this episode. So, the question that we are looking at here is the molecular shape and geometry. So what are they? Basically, every molecule has a different, has a kind of shape, a different shape, or we call them geometry in science. And why are they important to learn? Well, knowing about the shape or the geometry of the molecule, you can tell how you can predict how they interact with other molecules, or the same molecule, but the same kind of molecules. So you can predict like how their interactions will be, how their hydrogen bondings, how their intermolecular forces will be, how their intramolecular forces will be as well. Right. So, let's go into it. It's not too hard, to be honest with you. This part is quite basic. Now, let me just go a little bit back to my channel. I need to check something. Just a little bit. Right, so I've already done the video on intermolecular forces and type of bondings before. So this one should be episode 9. Right, so this one is episode 9. Okay, let's first start with molecular shape now. So how do we tell how the molecule looks like in space? I mean in 3-dimensional structure. So normally if we draw it, it would be in the same plane, right? In like 2D, 2-dimensional, in a piece of paper or the board. But in reality, every molecule will exist in a 3D structure, 3-dimensional structure. So that's why I draw these things like this. So first of all, let me introduce to you like what is this line called and what is this dashed line. This is called a wedge. And what it means is that if I have, like, let's say methane, CH4, these two hydrogen, these kind of covalent bonding means like it in the same plane as the piece of paper or the board. So let's say this is a 2 hydrogen it has. And then one is, the wedge one is the one like pointing toward you, and another one is the green one is the one that pointing away from you. This is the dashed line here. So the two things are basically on the same plane. The one here are pointing toward you, and another one is pointing away from you. So that's what it is. These kind of wedge and dashed line. Now, so in 3D structure, of course, things look a bit different compared to in 2D structure. So let's start first with methane now. So methane, why methane? CH4, it is such a fundamental, it's a very general, easy kind of molecule. One of the easiest organic chemistry molecule, yes, methane. And so the question now here is, how do I know that methane has this kind of structure? First, you have to identify what is the central atom. I'm sorry, in my other videos I say atom, but no, it's wrong, it's atom, okay? So you have to identify the central atom, and in this case, you cannot go wrong, because in this case, carbon is the central atom. So surrounding it, you have 4 hydrogen. But the question here is, how do you know that methane will have this kind of structure? Why it should not have other kind of structure? Well, so there is a rules for the bonding that you must know, which is like, you know, the bonding is made out of electrons, isn't it? It's made of electrons. And this one is also made out of electron as well. And you know, electrons, they repel each other, right? They repel each other. They do not attract, they repel each other, okay? So in that way, the distance or the bond angle, this was called a bond angle, okay? The angle of the bond between the two connection, or like the bonding, must be as far apart as possible from each other. So basically, the bonding between them must be as far apart from each other because they repel each other. Simple stuff, right? Simple thing. Well, by experiment, we managed to find out that methane has this kind of structure. And so basically, one, it's the two bondings are 109 degrees apart from each other. 109 degrees apart from each other. And also one is pointing toward you and one is pointing away from you. This one is away from you. Okay. So now, by experiment, we figure out it's this one, this bonding is 109.5 degree. So, of course, this one is also 109.5, this one also 109.5, this one also 109.5. So they must be equal. In case that all the 4s are hydrogen, they are kind of like symmetrical. I mean, they are evenly distributed. They are evenly distributed. So they must be 109.5. Okay. So what is the shape of this molecule of methane now? So basically they create a shape that looks like that has 4 sides. 1 side, 2 sides, 3 sides, and the last one down here is a 4th side. So 4 sides. That's why it's called tetrahedral shape and geometry. So methane has a tetrahedral geometry. Now, as we move on to other molecules, we can learn more about how things are different. Now, let's move on to ammonia, NH3. Which group does nitrogen, the central atom, belong to? Group 5, right? So, group 5, so surrounding the nitrogens, you have 5 electrons. Now, every of these bonds, the nitrogen contribute 1 electron. So 1, 2, 3, so it has 2 left, isn't it? The 2 electrons will remain here as lone pair. So they are lone pairs. So then, and the ammonia now has only 1 lone pair. And by experiment again, we figure out that for every lone pair, if you see it, if there's a 1 lone pair, it decreases the bond angle by 2.5 degree. So from 109.5 minus 2.5, you have 107. 107 degree, 107 degree. Of course, this bonding is between the NH here and NH there. And this can also be 107 as well. And between this hydrogen and that hydrogen, because they are in space, they look far apart, but between them you also have 107 as well. So it's like this. So it's like this. So the top you have two lone pairs, and the bottom you have like H, H, H here. So between them it's 107. This one also 107, and that one also 107 as well, you know. All right. So how will the shape or geometry of ammonia be? So since now we have something like this. It looks like a pyramid, isn't it? Look like a pyramid, isn't it? Okay, so basically it is different from the methane because the methane has 4 hydrogens surrounding it, and the carbon is in the center. So we call this structure tetrahedral, but for ammonia, the nitrogen, it's not exactly in the center, because over here there's no atom of any other element. So now we cannot call this structure tetrahedral again, because before it's like this. Before it was like this, but now it's like that. So it's a different shape now. You have to name it differently. Trigonal Bipyramidal. But why? Now let's look at this one. The nitrogen here is the top of the pyramid, isn't it? And the hydrogen here will be there, and the hydrogen there will be here. And then here it's, if I draw it right, it's gonna look like this. Now, so you see the base of this pyramid. It's a triangle, isn't it? The base is a triangle. And the whole shape represents a pyramid. That's why the name is Trigonal Bipyramidal for the geometry of ammonia. And it's different from the tetrahedral, because for tetrahedral the center atom is a carbon, but for ammonia, nitrogen is not exactly the central atom. Okay? Now, let's move on to water, H2O. So water is in which group in the periodic table? Group 6A. So it has 6 electrons on the outermost shell. So 1 electron is for this one, another one is for this one, so it has 4 left. So those 4 electrons left will become 2 lone pairs on the water. Now, if 1 lone pair decreases the bond angle by 2.5, 2 lone pairs by experiment, we saw that it decreases the bond angle by 5 degrees. So this one, 109.5 minus 5 will be 104.5. So you have only this bond angle now. There's nothing left to compare. See, the reason why the lone pairs pushes, let's say, why the presence of a lone pair pushes the bond closer to each other? Well, there has been some explanation about it. There has been certain theory about it, but they say that because the presence of the lone pair, it basically is very strong. It's two electrons there, 2 electrons there. It repels the electron from these bondings, so it kind of pushes the bond angle to decrease. So these 2 lone pair actually pushes the bond angle down to 104.5, you see. Now, so what is the shape or geometry? The shape of the water is now called bent. It's bent. It's an adjective. So you know the verb to bend, right? And now it's an adjective, it's bent. Okay. Now, so it's bent. Right, because basically, normally it's like this. Linear, it's linear. Linear. And now it's being bent. To look like that. Bent. So bending of the linear to become like bent shape. Okay, we will do a few more later. Okay, but I would like to go to other examples. Now, let's look at phosphorus pentachloride. Phosphorus pentachloride, of course, PCl5. Let's look at the structure now. How do we ensure that the bond angle between the bonds are the maximum? Well, by experiment again, we find out that this is how it looks like. So let me take another one. Okay, so basically, now let me just take this. Okay, so by experiment, we found out that this is the base. I mean, this is how it looks like here. And then one on top, one at the bottom. It's like one on top, one at the bottom. So it looks like this. And because this one is like a base and it's planar, it's in the same plane. So this one is 120, 120, 120. So this one is 120. That one is 120. And that one is also 120. However, because there's one on top, one down here, so the bond angle between this one and that one is, yes, 90 degree. That one and that one is also 90 degree. That one and that one is of course also 90 degree as well. So this is 90 degree to this, to that, and to that one. Of course, these two chloride will be linear, so they are 180 degree apart. 180 degree apart. Okay. Now, that is the bond. That is the thing about bond angle. What is the name of the shape and geometry of this molecule? Now, so basically, the base you see it's the base here. It's a say. Oh my God! I need a new pen. The base here. The base here is a triangle, and you see on top of that you basically have two more things. Okay, this is the top, and you have also one from the bottom. Right, so what does it look like? This structure has a base of a triangle, and it represents two pyramids on top of each other. So one pyramid here, another pyramid down here. Two pyramids on each other. So we call them Trigonal Bipyramidal. Now, easy to understand, isn't it? Now, let's move on to the next one, but let me just have some of my tea. Now, sulfur hexachloride. How do you know how they look like? Basically, there are 6 chlorides surrounding the sulfur central atom, isn't it? What group does sulfur belongs to? 6A. So you can see sulfur donates all 6 of its electrons to form the bonding with the chlorides, right? So it means the sulfur here has no lone pair left. 0 lone pair left. So we don't have to worry about lone pairs in this case. Now, so what is the best arrangement to ensure that the bond angle between them are maximum? Okay, let's look at this one. I need another pen. So they will form a kind of structure like, oh my god. Okay, let's just make it simple like this. Okay, right, so a base is looking like that, and you have one on top, and one on the bottom. So it looks like this. The base is the square, and one on top, one down here. So how do you name these? How do you name this structure? Can you name them square bipyramidal? Because they are made of a square base, and it looks like two pyramids on top of each other. Well, I thought the same when I was learning it, but no, the name is now octahedral. We don't say square pyramidal. We don't say square bipyramidal. We say octahedral, which means it has 8 sides. Look at this one. The pyramid on the top actually creates 4 sides, you can see. And the one down here, it creates another 4. So that's why this structure is called octahedral, 8 sides. Alright, that is the basic. Now maybe let's look at other examples and we can do some exercise, shall we? Alright, so try some examples I have already prepared for you here. Sorry, my voice not so good because I've been making videos a lot. Now, so this one, please try carbon dioxide, dihydrogen sulfide, formaldehyde I've already drawn for you, phosphorus trichloride, and hydrogen nitrate. Please pause the video for like say 5 to 10 minutes and then work on this one, and you can come back later for the result, okay? Alright, I'll give you the result now. So, carbon dioxide. Of course, the carbon will be the central atom in here. So, you have C and then 2 hydrogens surrounding it. Okay, the question here is, carbon is in group 4, isn't it? Oxygen is in group 6. So oxygen needs 2 more electrons to have a full octet. So of course it would be like this. It would need 2 electrons from the carbon. So it will form a double bond here. And also here it will need 2 more electrons from the carbon to form another double bond with the other oxygen. So here oxygen will have, of course, 2 lone pairs left. 2 lone pairs left there because oxygen group 6, right? 2 electrons there, and then 4, 6. This one is already like 4 plus 2 is 6. And here the carbon all donate like 4 of its electrons in here. Now, so now the carbon has no more electrons left to even form any lone pair. So you can see here, no lone pair at all. So the question is, what is the bond angle that ensures the maximum distance between the bonds? Is it like this? No, it's like that. This is the one that ensures the maximum distance between the bonding. And the bond angle is of course 180 degree. 180 degree. Oh, I should have used blue. Let's use blue here. So 180 degree. 180 degree. And this kind of shape and geometry, we call them linear. I mean, some people they say linear, but no, it's linear. It's linear. Linear. Because it represents a line. You know, a line. And the adjective form is linear. Okay, so linear. So look at hydrogen sulfide for a moment. You might know already the sulfur is the central atom. And sulfur is in group 6, right? So for every of these hydrogen, it gives away 1 electrons to form the bonding. However, it still have 4 electrons left, so it will become 2 lone pairs. And this is very similar to water, exactly, H2O, because oxygen and sulfur are both in group 6A. Now, because of 2 lone pairs, can you guess what is the bond angle between like these SH and SH bond? Okay, let's start from methane, 109.5. And then minus, you have 2 lone pairs, so minus 5 degrees. So now this bond angle should be 104.5 degrees. 104.5. Very good. Now, let's move on to the next case. Oh wait, I haven't named what is the shape and geometry of this molecule. It's the same like water, so it's linear. Sorry, not linear. Sorry, it's bent. It's bent. Now, how about formaldehyde or methanol? If you want it that way. So formaldehyde, as the oxygen's 2 electrons there, so they still have 2 more. However, it is the central atom that is the most important. And the central atom is carbon, is surrounded by 3 things. And the central atom, the carbon, does not have any lone pairs left. So, so what is the bond angle to ensure the maximum distance between the bonds is this one. Same plane, 120 degrees apart from each other. So this bond angle should be 120 degrees. This one also 120. This one also 120 degrees. Now, so let's move on to the next case of phosphorus trichloride. I know we did phosphorus pentachloride before, PeCl5, but now let's try PeCl3. Now, of course, the central atom is phosphorus, group 5, and it gives away 1 electrons for each chloride, so it still have a lone pairs left. And now the situation is like this: one bond actually away from us, another bonding is toward us, is pointing toward us, and another bond it's like, you know, not toward us but not away from us. It's on the same plane as this board, you know. And so with 1 lone pair from the phosphorus, it pushes this bonding down to how much? 109.5 minus 2.5, it's 107 degrees. You guessed it right. So this one is also 107, and this bonding and that one, it's also 107, because in space, you know, it's like that. It's like that. This one 107, that one 107, and that one also 107. Okay. Okay, so how's the shape? What is the shape now and geometry? Because phosphorus is not exactly in the center, so we cannot say that this one is tetrahedral like in the case of methane. But now it looks like a pyramid with a base of a triangle. So the the shape and geometry should be trigonal pyramidal. Trigonal pyramidal. And the last one, hydrogen nitrate, should be the most difficult. Well, it's you can see that this is an acid, right? And an acid like that, the hydrogen would probably be attached to an oxygen, which is a highly electronegative atom. So you know that oxygen will be attached to hydrogen already? Yes. And you have 3 of them, and you have the nitrogen. So the good bet now is, of course, nitrogen is a central atom. So let's say nitrogen central atom, and you have 3 you have 3 oxygens surrounding it. So yes, that's one. Okay, so oxygen is in group 6, so it demands 2 more electrons to be stable octet, each of them. So it will have to take away 2 electrons from the nitrogen. And now, this one will form a double bond. The nitrogen donates 2 here, 2 there, and 1 here. So yeah, that's exactly 5. That's exactly how much it has, the nitrogen, group 5, yeah? And then this one, yeah, it's finished. So of course, these oxygens still have 2 lone pairs there, 2 lone pairs there, 2 lone pairs there. And the effect of the lone pairs here is very similar to water. So, oh, this one is not even a covalent bond. This one is more or less like, you know, hydrogen, I would say. Anyway, the bond angle between these things, well, because this bond is a double bond and this one is single bond, so I don't think it's exactly 120. You have to determine like experimentally, because this bonding, the double bond and this single bond, is not the same. So you cannot say that this is 120, 120, 120, okay? You can guess like that, but I don't think it's 120. Anyway, so what is the shape of this whole molecule? You can see that the molecule now has a weird shape. It's like this. It's like, it has a weird shape, like this one pointing up, and this one it's in the middle, and then normally we would not determine the shape of something that complicated anymore. So that's why I do not give you like more complicated exercises. Anyway, okay, that's it. Okay, that's it for this video, I think. Thank you so much for watching. Please like, share this video with your friends, subscribe to my YouTube channel, and press on the bell button next to the subscribe button so you can get notified about my new uploads, okay? You can also follow my Facebook, but please don't add me on Facebook, okay? Don't add me as friend on Facebook. Thank you, and see you in my next video. Bye-bye.